Hello friends, in this video we are going to discuss about the minority carrier distribution in a bipolar junction transistor. For this case, we will consider a NPN transistor. We know that originally a NPN transistor is N plus plus P plus and N transistor. So if we look at the cross section of an NPN transistor, so the original cross section, so this figure is the cross sectional view of NPN transistor. So this part is the N plus plus region, and this is the P plus region, and this is the N region. So terminal with the N plus plus region is the emitter region. The region and the terminal at the P plus region is the base region, and the terminal at the N region is the third region. So originally the cross-sectional view of the NPN transistor, and we know that the electrons will flow from the N plus plus region towards the collector region in this fashion, like this. So this is the flow of electrons that are coming from the emitter region to the collector. Now, for the simplicity purpose, what we will do, we will simplify this diagram like below for the simplicity of the analysis. For that, we will consider only this part of the cross section. We have already discussed about this cross sectional view. So if we consider this dotted region only, then this dotted region can be drawn like this. It will look like a rectangular view, and in this rectangular view we will have our emitter region like this. We will have our base region like this. This is the N plus plus region, this is the P plus region, and this is the N region. And here we have our terminal emitter, and here we will have our collector terminal. This is our collector terminal at the inside, and at the P plus we will have our base terminal. So this is the simplified structure that we can get from this structure. So we'll use this structure, this simplified structure for the analysis. And this simplified structure, if it is drawn in a horizontal view, it will look like this. This will be the horizontal view. So this part will be the N plus plus region. Hence, this terminal will be the emitter. This part, the middle portion, is the P plus region, and this portion is the N region. So we can say this will be the base terminal, and this will be the collector terminal. And as we know that this junction is the emitter junction JE, and this junction the collector junction JC. So if we want to operate this transistor into active region or forward active region, then we have to make this junction JE as forward bias. If we want to make the forward bias JE, then we have to apply a negative potential here and a positive potential here. It will make the JE junction forward bias. Similarly, if we want to make the JC junction reverse bias, then the collector terminal should be given a positive polarity and the base terminal will be given a negative polarity. This will make the JC junction reverse bias. Due to this, what will happen in the emitter? The electrons, which are the majority carriers of the emitter, they will try to follow this direction, and since the JE junction is forward bias, since electrons are the majority carriers, so they can cross this junction, JE junction. When this is one type of majority carriers that are flowing from the emitter to the base. Similarly, in the P plus region, that is in the base region, we have majority carrier as holes. So holes will be the majority carriers of the base region, and since the JE junction is forward bias, so these holes will cross the JE junction and come into the emitter region. So these are the majority carriers that will flow across the JE junction. Now for this we can say that when the emitter is injecting electrons into the base, so these electrons when they enter into the base region, they will become the minority carriers, and the holes which are injecting from the base region into the emitter region, they will become the minority carrier inside the emitter. So the sign signifies, dotted line signifies that it is the minority carrier right now. So we can say that since the emitter is highly doped than the base region, so the minority carrier concentration at the edge of the JE junction, the base, will be very high with respect to the minority carrier concentration at the emitter at the edge of the JE junction. So let us assume that the JE junction has the minority carrier concentration like this. So we can say another thing, we can say that here since the JC junction is reverse bias, so you can see the depletion region here is very wider for the JC junction, but here the depletion width at the JE junction is thinner with respect to the JC junction. Now the minority carrier concentration in the base, if we draw, and we know the minority carrier concentration that are coming from the emitter into the base has a very high value at the edge of the emitter. So let us denote this as this point, because we are plotting the minority carrier distribution. Similarly, the minority carrier concentration, that is the whole concentration at the edge of the JE junction in the emitter, is like this. It will be small value with respect to this minority carrier concentration in the base, we can say it will have a small value like this, since the base is lightly doped with respect to the emitter. Now, since the base width, if we denote the base width like this, so if this is the width of the base region, this region is the width of the base region WB, and this width of the base region, we know during the fabrication of the BJT, the width of the base region will be very much less than the diffusion length of the electrons of the minority carrier inside the base, where LB is the diffusion length of electrons inside the base, and the width of the base region should be very small with respect to the length of the diffusion for the electrons. That's why what will happen, the electrons which are injected from the emitter and come into the base and become the minority carrier, they will diffuse to this base region. When the diffusion happens, they will diffuse exponentially like this fashion throughout the length of the base region. Again, the hole which are coming from the base into the emitter, they has become the minority carrier, so they will also diffuse in this fashion like this. These are the concentration profile inside the bipolar junction transistor emitter and base of the minority carrier. Similarly, in the collector region, the collector region will have a n-type doping. Since it has a n-type doping, there will be some minority carriers here. So the minority carriers here are the holes that are the minority carriers. And we also know that since the JC junction is reverse bias, that's why the electric field within the junction will be directed from N to P like this fashion. So the electrons which has came from the emitter to the base, and they are diffusing throughout the length of the base, when they come inside the depletion region of JC, they can see there is a favorable electric field, so they will cross the junction and come into the emitter. They will come into the collector region like this, because the JC junction is reverse bias and the electrons are flowing in this direction, which is there is a favorable electric field inside the JC junction, so the electron can cross the JC junction. So now, if we see the minority carrier concentration inside the collector region, then we can say that at the edge of the JC junction, there will be high concentration of electrons, because the electrons are coming from the base to collector. So at this edge of JC junction, there will be high recombination of electron and holes, because there are some minority carrier holes present inside the collector. That's why the minority carrier concentration at the edge of the JC junction in the collector will be low than the farther distance from the, because at the edge of the JC junction the recombination of the electron and holes are taking place. That's why the minority carrier concentration at the edge will be small, and if we go away from the JC junction edge, then the minority carrier distribution will be higher and it will be constant. So we can say these are the minority carrier distribution profile inside the emitter, base, and collector. Now, originally, the minority carrier concentration profile within the base region has an exponential plot like this, but to make the calculation simpler, we will assume that the concentration will decay linearly like this. So what we can say that if we now write, see the current direction, the current will be, there will be a total current IE this direction. This is the IE current, and this IE current constitutes of part. One current is due to the electrons which are flowing from the emitter to the base. So let us denote that current as I N E, and there is also some current due to the holes which are coming from the base to the emitter. So there will be another current component, and that current component is due to the holes that are coming from the base to the emitter. Let us denote this as IPE. Similarly, in the collector region, we will have a total collector current like this. In this direction, the inward current IC. So this is the inward current IC, and this inward current IC consists of the electrons which are coming from the base to collector, and this is called as INC. And there are some current due to the minority carrier. We are neglecting this. So these are the current that can flow inside the semiconductor bipolar junction transistor. The minority carrier concentration 5 inside the semiconductor bipolar junction transistor at the active region of operation, and the concentration of the electron at this point, if we denote this as concentration of electrons in the NB, that is the in the base region, that is NB. NB can be defined as NB0 exponential BBE by BT, and NB0 is the electron concentration at the base at x equals to. Similarly, we can also find the current of INC from this concentration, but we are concentrating on the minority carrier profile. That's why we only stop our discussion with respect to the concentration only. Now let us go for the another mode of operation. That the another mode of operation that we have is the cutoff region of operation. So for cutoff region of operation, we know the JE junction should be reverse bias and the JC junction should also be reverse bias. Let us see how. This is our N plus, E plus, and N that is the NPN transistor. This is the emitter, this is our base, and this is the collector. This is the JC junction, and this is the JE junction. Now to make this JE junction, because we want to operate the transistor in the cutoff region of operation. To make the cutoff region of operation, we know the JE junction should be reverse bias and JC junction should also be reverse bias. So to make the JE junction reverse bias, we know that this emitter should be given a positive potential here and a negative potential here. Similarly, the collector terminal should be given a positive potential here and a negative potential at the base to make the JC junction reverse bias. So when the JE and JC will be reverse bias, this depletion region of the JE will be increased. So let us draw the depletion region like this. This will be the depletion region right now, because the depletion region has now increased due to the reverse bias of the JE junction. So this is now the depletion region WD at the JE junction, because the JE junction has been reverse biased, so the depletion region has been increased. So right now, what will happen? There will be some electrons here, the majority carriers. There will be also holes, which are the majority carriers at the base, and there will be electrons, the collector, which are the majority. Now, due to the JE junction, which is a reverse bias operation, so this electron cannot cross the JE junction because it is a reverse bias, and within the reverse bias, we know the electric field will be directed from the N side to the P side like this. So this electron of the emitter region cannot cross this JE junction. Similarly, the holes, which are the majority carriers of the base, they cannot cross this JE junction. So this is not possible for the hole, and this motion is also not possible for the electrons inside the emitter. But what will happen? There will be some electrons here, and since it is a N++ doping, then we know there will be some amount of holes that will also be present, since this emitter region is highly doped with N++, so there must be some minority carrier holes. These minority carrier hole here, similarly there will be some minority carrier electrons also there. So there are some minority carrier electrons, and there will be some minority carrier holes inside the collector region. So if we draw the minority carrier profile, then the minority carrier profile, since the JE junction is reverse bias, the minority carrier profile will look like this. So the minority carrier profile at the emitter will look like this, and the minority carrier profile of the collector region will also look like this. It will have a high value than the emitter because it is lightly doped at the collector. That's why the minority carrier concentration is high here with respect to the emitter, and the minority carrier concentration at the base region will like this. So this is the minority carrier concentration, that is whole of the emitter, which is changing with respect to x, and this is the minority carrier concentration, that is the electron concentration within the base, which is changing with respect to x, and this is the minority carrier concentration, that is p, that is whole within the collector with respect to x, and this is the thermal equilibrium value of the concentration of the holes in the emitter. Let us denote it as PE0. Similarly, there will be a minority carrier concentration at the thermal equilibrium value, and this thermal equilibrium value is NP0, and in the collector like this, so it is the PC, that is. So if we draw the minority carrier concentration profile inside the emitter, so at equilibrium, the minority carrier concentration profile at the emitter will be like this value. So let us denote it as PE0, and the base region is slightly doped with comparison to the emitter. So the minority carrier concentration profile will be higher here inside the base than the emitter, and here it will be NP0, and the minority carrier concentration profile inside the collector will be higher than the base, because the collector region is lightly doped with respect to the base. So it will be PC0. Now, after applying the bias, what will happen? After applying the bias, the minority carrier concentration profile will vary like this inside the emitter, and the minority carrier concentration profile inside the collector will vary like this, and the minority carrier concentration profile inside the collector will be like this. So this is the base region minority carrier, and the base region minority carrier can be defined by NB, electron in the base changing with respect to x, and holes in the electron changing with respect to x, and this is the holes inside the collector changing with respect to x. So this red line graph is the minority carrier distribution in an NPN transistor at the cutoff region. Now let us discuss what will be the minority carrier concentration profile inside the NPN transistor at saturation region of operation. So at saturation, we know that since it is a N++ emitter, and it will be in region of the collector, and this is the base, which is P plus region. There is a JE junction here, and this is the JC collector junction here. So for saturation region of operation, we know we have to make the JE junction forward bias as well as the JC junction also forward. For that, we have to give a negative potential at the emitter and a positive potential at the base. It will make the JE junction forward bias. Similarly, if we apply a negative potential at the collector and the base is of negative positive potential, then this will give the JC junction forward bias. When the both the JE and JC junction is forward bias, we know that the depletion width of the JC junction will be thinner and the depletion width at the JE junction will also be thin. Now, the electrons which are in the emitter as the majority carriers, they can cross the junction like this and they can come into the base as the minority carrier, and these electrons will diffuse through the base length because the base region width is smaller than the diffusion length width of the electron. So we can say the electrons which are coming from the emitter to the base and becomes the minority carrier, they will diffuse by the length like this, and there will be some amount of holes. There will be majority carrier inside the base, and these holes can also cross this J junction and become the minority carrier in the emitter region. So the holes can also, so there will be a minority carrier distribution, they will also diffuse, so they will diffuse. Similarly, in the collector region, you can see that since the JC junction is forward biased, that's why the holes of the base region can cross this junction and become the minority carrier inside the collector. So that's why the minority carrier distribution will look like this in the collector region. So we can say that this is the minority carrier concentration, that is the whole concentration inside the collector, which is changing with respect to x, and this value is the thermal equilibrium minority carrier, that is the P0. Similarly, in the base region, this blue graph is the minority carrier concentration within the base, that is the electron concentration within the base, and B changing with respect to x. So the minor, and this dotted line is the minority carrier concentration profile at the thermal equilibrium concentration in B0, and in the emitter the minority carrier concentration will look like this. So this is the minority carrier concentration inside the emitter, and it will look like this. This is the P, that is the whole concentration in the emitter changing with respect to distance x, and this is PE0, that is the equilibrium minority carrier concentration. Now this is the saturation region operation of the NPN transistor, where the minority carriers are distributed like this. This is all about the minority carrier distribution in all the regions. Say, and in this way, the minority carriers will be distributed within the emitter, base, and the collector at different region of operation. Thank you.